Okay, so today we're going to talk about chapter 9.1. Chapter 9 is the second part of inference. So we were going to take from a population, we're going to take a survey, and we're going to find out what's going on with that. The first, in chapter 8, we talked about confidence interval, how to construct a confidence interval. Okay, so in 8.1, we talked about the basics. 8.2, we talked about how to do a confidence interval for a proportion, and then in 8.3 we did constructing a confidence interval for a mean. Okay, we're going to do the same thing here, except instead of confidence intervals, we're going to do significance testing. Okay, so in significance testing in 9.1 we'll do the basics. 9.2 we'll talk about how to do a significance testing for a proportion, and then in 9.3 we'll do a significance testing of a mean. Okay? All right. So, 9.1, let's talk about how to do what a significance testing is, or significant testing, okay? So, let's go back to way back when we talked about the free throw shooter. A guy came into the gym, said, yeah, I'm an 80% free throw shooter. We hand him the ball, he starts doing, shoot 50 of them, and out of the 50, he gets 32, he makes 32. Okay? So this is basically a 64% free throw shooting performance, right? And so this would be our P hat, since it is that one sample, right? So that's the P hat. Okay, what we're trying to find is the true proportion of what is his true free throw shooting, right? So we're in significance testing, we are not so much talking about, in confidence interval we said, well, it's going to be between this and this, okay? But in significance testing, we're really going to say it's yes or no, okay? All right. So, we did 64%. So, what's happening here? We have 64%. So is the guy an 80% free throw shooter or not? So what are the two possibilities? The two possibilities is that yes, he is an 80% free throw shooter having an off day, all right? Or the second probability is no, he's actually not an 80% free throw shooter, okay? So what we do is we run a simulation. So we're going to do a computer simulation, and we're going to do 500 of these, okay? Or it's 400 of these. So let's say that I actually was an 80% free throw shooter. Okay, and if I did 400 simulations, we get a dot plot on page 553. And it shows you there. And if you look at the dot plots there, okay, it looks like at around 80% is where the median is, and it's roughly symmetrical across 80%, what you expect it to be, right? Okay, so let's go see and look at where 0.64 is located in there. Okay, if you look at 0.64, there are only 3 dots that are equal to or less than 64%. Okay, which means that out of the 400 simulations that we did, there were 3. So that is less than 1% of the time. So less than 1% of the time, you're going to have an off day, and you're going to shoot less than 64%. So, is this statistically significant? Okay, remember we talked about statistically significant when we agreed way back when that 5% was statistically significant. So this is less than the 5%. Which means that it is so far off the norm that yes, this is statistically significant, okay? And the chances of this guy being an 80% free throw shooter are very, very slim, okay? All right, so let's go to page 554 and actually go to 9.1, and we're going to talk about hypotheses, okay? So the hypotheses here is what the guy said. The guy said that my hypothesis is that my free throw shooting is 80%. Okay, so this is what we call the null hypothesis. The null hypothesis Then we have the alternative hypothesis, and this is what we're trying to prove, is that no, you are a less than 80% free throw shooter. So again, the alternative, there are two hypotheses. One is the null hypothesis, one is the alternate hypothesis, right? So the alternative hypothesis is that no, you are less than, this is what we're trying to prove. So the alternate hypothesis is what we're going to try to prove. The null hypothesis is what is stated. Okay, all right. So if you look at the definition on the green box of page 554, it says that the alternative hypothesis is the claim that we are trying to find evidence for. So we're trying to find evidence for this. Okay, so we have one sample that gives us a little bit of hint that that might be true, but we're trying to actually prove it. Okay. So the null hypothesis is what they actually state, okay? So if you look at the green box, it says that the claim that we weigh evidence against is the null hypothesis. So the ho and the ha, okay? All right? So if you look at page 55, there's another green box there. So here we are talking about, here we're talking about like this and 0.8, and we are on this side over here. So this is a one-sided. In other words, P is less than 0.8. Okay, there are times where it's going to be the other way, right? And it could be this way, all right? But either way, those are both one-sided hypotheses, right? They are one-sided hypotheses. Okay, there are going to be times when you're going to find something that is going to look like that. So in other words, it doesn't really matter which side it resides on, as long as it's not that guy, we're okay. And that's what we're going to try to prove. Okay. So this would be a two-sided thing because it could be residing on either side. Okay. But when we're talking about over here, like that, that is a one-sided alternative hypothesis. Okay. So let's look at that example there. It says juicy pineapples. At the Hawaii Pineapple Company, managers are interested in the size of pineapples grown in the company fields. Last year, the mean weight of the harvest was 31 ounces. A different irrigation system was installed in the field after growing season. Managers wondered if this change will affect the mean weight. Okay, so the hypothesis is that the mean weight is 31. The alternative, the hypothesis, the ha, would be that the mean weight is not 31. Okay, so this would be a two-sided alternative hypothesis here. Okay? Okay. Let's move on to, let's go ahead and say, let's find out what a p-value is, okay? So let's go back to the example that we were talking about here, okay? So here we were talking about, the P was 0.8, the Ha was less than 0.8, okay, and we found that out of the 400 simulations we did, only 3 had less than or equal to 0.64, okay. This here is what we call the p-value. This is what we call the p-value. The p-value here, okay, the p-value is, so if you look at the p-value definition of the p-value of a test is the probability of getting evidence for the alternate hypothesis, okay, as strong or stronger than the observed evidence when the null hypothesis is true. So when the null hypothesis is true, the probability of getting something that would say that the Ha is true. Okay, all right? So the smaller the p-value, okay, the greater chance that the Ha is correct. Okay? So in other words, we have a greater chance that the Ha is good and the Ho is bad, okay, if the p-value is small. When the p-value is large, that means that we have more evidence towards the ho and less towards the ha. Okay? All right. So let's go and see if we can do an example there. Healthy bones. Calcium is a vital nutrient for healthy bones and teeth. NIH recommends a calcium intake of 1,300 milligrams per day. NIH is concerned that teenagers are not getting enough calcium. Okay, the researchers performed a test that the average intake of, so we're doing a mean is 1,300, and they're worried that they're not getting enough, so the ha would look like that. Okay? Okay. The researchers then compute the calcium intake for each student. Data analysis reveals that we get a X bar of 1198 milligram with a standard deviation of 411 milligrams. Researchers performed significance testing and obtained a p-value of 0.1404. 0.1404. So we did this, and they found a p-value of 0.1404. Okay. In other words, this is 14%, 14.04%. Okay. So, A, explain what it would mean for the null hypothesis to be true in this setting. So, if the null hypothesis was true in this setting, that means that the average intake of the calcium for the teenagers are 1,300 milligrams. Okay? All right. So, what does the solution say? If that means at the end, okay, we're good with that. B, interpret the p-value. Interpret the p-value. So the p-value is 14.04. That means that the evidence for the alternative hypothesis, which is the mean is less than 13 milligrams per day, is 14.4%. Okay? So, that would be the p-value. So assuming that the mean daily calcium intake in the teen population is 1,300 milligram, there is a 14.04 probability of getting a sample mean of 1198 milligrams or less just by chance. Okay? All right. So making conclusions. So what do we say here? Okay? 14%. So is this statistically significant? This is not statistically significant because it is greater than the 5%. Remember, we want this p-value to be smaller, the p-value to be small. When the p-value is small, we can say that this is the one we're going to go with. Okay? All right? But the p-value here is large enough that we can't do that because it's greater than 5%, right? Okay. So let's go to page 558, making conclusions, okay? So the significance levels, okay? If there is no stated significance level, we are always going to default to the 5%, right? Sometimes we do a significance level of 1% or 10%, or they can change that. But if there's no mention in it, in the actual question, then you're going to go with 5%, okay? So definition, the green box on page 558, significance level, it says, significance level alpha, the significance level alpha is the value that we use as a boundary for deciding whether the observed data it can happen by chance and then the null hypothesis is true. In other words, if we're going to compare the p-value, you're going to compare the p-value to the alpha, the significance level, okay? And we want the p-value to be smaller than the alpha, right? Then we can go and say that we have evidence for the ha, okay? Because if the p-value is greater than the alpha, okay, then we say we do not have, so we go with, we cannot reject this, right? Okay, all right, so here we go. Okay, so we're going to do either one or two things, okay? So this is the one thing that you need to get out of today, okay? This is the one thing that you need to remember, okay? So, we're going to do a significance testing if the p-value the p-value is less than alpha, okay, we're going to fail to reject the hoe, okay? Where are we at? No, we're going to reject the hoe. I'm sorry, we're going to reject the hoe. We are going to reject the hoe, and we have evidence for the ha. Okay. So 3 out of 400, the free throws, less than 5%, so p-value is less than alpha. So we reject the null hypothesis that the probability is 0.8, and we have evidence for the proportion being less than 0.8. Okay? If the p-value is greater than alpha, then we fail to reject the hoe, and we don't have evidence for the ha. Okay? So notice that we do not accept the hoe. We never accept the hoe. We either reject the hoe or we fail to reject the hoe. So when p-value is greater than alpha, we fail to reject the hoe, and we do not have enough evidence for the ha. Okay? So fail to reject. Okay, this is kind of like when you're on trial for a murder, right? Okay, you are proven to guilty. Okay, so when they do the trials, they do not say that you are innocent. They say that there's not enough evidence to convict you, right? So that's the same kind of thing that we're doing here. We are failing to reject the hoe, okay? All right, so this is the one thing you want to remember. The p-value, so we want the p-value to be less than alpha, so they can reject the hoe and say that we have evidence for the ha, because evidence for the ha is what we're trying to prove, right? Okay. So when the p-value is greater than alpha, you can't do that, and so you fail to reject the hoe, and you don't have evidence for the ha. All right. So let's go ahead and do that example where it says better batteries. So let's do the better batteries example. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular one. However, these batteries are more expensive to produce, so the company would like to convince that they really do last longer. So, based on anything the company knows, the company selects a simple random sample of 15 deluxe batteries and uses them continuously until they are completely drained. The sample mean lifetime is 33.93. A significance level testing is performed using the hypotheses. So we have the hoe is mu is equal to 30. So we have the hoe is mu is equal to 30. The ha is mu is greater than 30, right? Because this is what we're trying to prove, right? This is what we're trying to prove. We want to say that it's longer than our regular batteries, right? And we do that, and we found that the resulting p-value is 7.17%. We found the p-value to be 7.17%. And what conclusion would you make if the alpha is 5%? So the alpha was given as 5%. So we're going to do the p-value, compare the p-value to the alpha, and what do we find? The p-value is greater than the alpha, alpha. P-value is greater than the alpha, which means that we failed to reject the whole. Failed to reject the whole. Not enough evidence. Not enough evidence for the ha. Okay, so we do not have enough evidence to say that the mean average lifetime is greater than 30, even though the random sample that we did was greater than, the mean was greater than 30. Okay? All right, so that's that, and we're going to stop right here today.